you'll have my little hints. So let's talk about this review. So a sound wave is a longitudinal wave. I believe there's a question on the test. Interesting about, can't spell longitudinal and talk. Um, Interesting about the sound unit is there's no quiz, it's just a test. Okay, so you don't have those quiz questions that sometimes are on the test to kind of give you an idea what the test questions are like. But there's a one question on the test I want to say, and it says something like, is a sound wave have troughs and crests, or does it have compressions and rarefactions? Well, since a sound wave is a longitudinal wave, it's going to have a compression and it's going to have a rarefaction. Okay, and then another important thing about sound wave is it's mechanical. Sound waves are mechanical waves, which means they require a medium. Okay, so then there's this question: is there sound in outer space? Well, outer space is just empty space, and I know air seems like empty space, but it's actually a gas. The air we're breathing is a gas. It's not really empty space, and so if there's empty space, there's nothing for the sound to travel on. There's no particles, and so no, there's no sound in outer space because it's empty, right? It's empty space. There's nothing for the mechanical sound wave to travel on. Okay. Now, the next one. So, audible sound is a frequency, and it's 20 to 20,000 hertz. There are some things as you get to know yourself and your study habits and what you're good at learning and what you're not good at learning. I know that I'm not good at learning numbers. For example, when I was in college, I originally started as a history major, believe it or not, and I realized I could remember facts all day long, tell you all about history, but I couldn't remember dates. And it turns out dates are kind of crucial to being a history major. So I had to change majors. Um, so if I was studying this unit, I would actually have to put it on a note card or something. 20 to 20,000 hertz is audible sound, and just rote memorize it. Um, then we can talk about frequencies, right? Audible sounds are frequency. Pitch, pitch is your frequency. So, for example, low frequencies, like if you sing bass or an instrument with a really low pitch, that's going to be a low frequency. And then if you have an instrument with a high pitch, that's going to be a high frequency. If you're singing, that would be like soprano. Soprano would have a higher frequency than bass. So pitch is kind of our music word for frequency, and frequency is kind of like our science word or our physics word for pitch. If you have a short air column, you're going to have a high pitch. And if you have a long air column, you're going to have a lower pitch. So the way I like to think about this is I like to think about a piccolo and a flute. If you play these instruments, I'm going to generalize them a little bit, and I know people that play those instruments hate that. For example, I had a student that played viola, and she would get so upset if we called it a violin. She's like, "They're so different." So I know there's some differences within a piccolo and a flute, but the big one to me is I think your mouth hole is here, but I'm not certain. 'Cause I don't play piccolo. So there's your piccolo, and then your flute is actually straight. It's not curved like this. A piccolo is, a flute is straight. I know that. your piccolo is just like a flute almost, except it's shorter. And so it plays higher pitched notes than a flute. And a flute, of course, plays high pitched notes, but a piccolo is even higher. So that's kind of the way I like to remember the short air column and the long air column, pitch and frequency thing. Now we can talk about infrasonic, audible, and ultrasonic. Audible, that's that 20 to 20,000 that we were talking about earlier. Okay, and then infrasonic is below 20. I'm really bad at writing with this pen, sorry. And then ultrasonic is above 20,000. So sound above what we can hear is ultrasonic, and sound below what you can hear is infrasonic. You may have heard of ultrasonic before with it, like an ultrasound. Okay, you don't have to have an ultrasound when you're pregnant. You can have an ultrasound because your doctor is trying to find a mass in your body, or, for example, I donated eggs, and so I had to get ultrasounds so the doctors could kind of see how many eggs, how fast they were growing, that kind of thing. So when you do ultrasound, let's just pretend we're doing a pregnant person. This is her belly. Okay, we put the ultrasound wand up to the belly. Okay, it's got like a cord or whatever. And what it does is the belly is full of liquid, right? This is all liquid. And so it sends sound back and forth, until it kind of picks up, where there is solid and where there's liquid, right? So this is our baby, okay, or our mass or whatever. It'd be an odd baby-shaped mass. But it's basically going to bounce off of this solid baby in this liquid, and give us a picture of our baby. It's kind of like sonar. An interesting thing is they have these ultrasounds now that you can get for your house, and you can kind of do that, and then you can like hear your baby's heartbeat or whatever all the time. But one of the things that they're not quite sure about is there hasn't been a lot of research on repetitive, like very often ultrasounds on the baby's hearing, right? Because the babies have ears. Sound travels fastest in sound in liquid, right? And this repetitive over and over and over ultrasound, how that affects the baby's hearing. There's some anecdotal stories that show that babies, people that use these ultrasound over and over and over at their house, their babies are kind of not immune to sound, but they talk very loud, and like, or loud things kind of bother them a lot and things like that. So there's not a lot of research done on this. So your regular routine ultrasounds and that kind of thing is not going to upset the baby or anything, but they're worried about, like, if you did it every day, if you did an ultrasound every day on your baby, how, or multiple times a day, how that might affect your baby. So then we talked about how pitch was our frequency. Well, intensity is a loudness. Okay, and loudness is relative. Okay, what I think is loud is maybe not what you think is loud. My dad is kind of losing his hearing a little bit, I think. I hope that's why. And he turns the TV on really, really loud. And so when I go visit him, he's got the TV on super loud, and it's like so loud it's like uncomfortable. It hurts my ears. And so it's loud to me, but he thinks it's great. It's perfect for him. And so that's relative. So then we have this intensity scale, which measures relative loudness, or it gives us a way to kind of discuss loudness in a way that is the same for everyone. And so the decibel scale is logarithmic, like the pH scale, just like something that has a pH of 2 is like, 10 times more acidic than something with a pH of 3. The same, see, I can't spell these big words while I'm talking. The same with the decibel scale. Something that has 2 decibels is going to be, 10 times less than something with 3 decibels. And so then we can talk about our threshold of hearing. Our threshold of hearing is 0 decibels. These numbers, again, they'd be something I'd have to put on a note card, just like my 20 to 20,000, in order to remember them for the test. I wouldn't be able to just, remember this just reading it once. Your minimum audible sound, this is kind of like whispering. That's about 20 decibels. Conversation is 65. You can get some apps on your phone, and they'll actually measure the decibel of the sound around you and tell you what it's similar to. So, like my students, I had some classes that were loud, and I would put this app up, and I'd say, look, here's loud as heavy traffic or whatever, to try and get them to be a little more quiet. And then your threshold of pain is about 120. That's also the threshold of that's also a rock concert. That's why a lot of people that are into sound and stuff, they say be careful with the rock concerts or wear like earplugs at a rock concert. That seems to kind of defeat the purpose of a rock concert to me, but it is what it is. So again, those are things that I would have to memorize. I would not just remember them. So then we can talk about noise. Noise is random. Okay, it's just random sounds. There's no rhyme or reason to them. They're just completely random. Okay, there's an interesting TED Talk about this guy makes like truly random music, and he uses like a number generator or something to pick sounds, and he writes like some music, but it's not music because it's truly random, and he plays it, and it's weird. So if you want to look up that TED Talk, it's pretty cool. And then music is non-random, right? Music has a recognizable pattern. That's why when we turn on the radio, we if we hear something, a song, we're like, oh yeah. You can, before even the person starts singing or anything, sometimes you can even tell what song it is because, it has that recognizable pattern. And part of that recognizable pattern, or part of music, is the beat. Sorry, not writing very well. Okay, so your beats are sounds that are set off from each other just so slightly. I used to make my kids calculate beats. It doesn't look like that you guys have to do that in your course. But like when we would calculate beats, the beat would be like 2 hertz or 4 hertz. They're very slightly set off from each other. If I was musically inclined, I could maybe like, when you beatbox something or whatever, they're just slightly set off from each other enough to kind of give you that nice rhythm, and again that recognizable pattern. Now the speed of sound is, if we want to talk about the speed of sound in different mediums, gas. If you think about particles, gas is our least dense medium, and then liquid is a little more dense than that. And then solids are the most dense. Okay, and since sound is a mechanical wave, the medium that it travels through, it affects it. Okay, affects the speed. And so the closer the particles are together, the faster it can travel. So that means a gas is going to be the slowest. And solid is going to be the fastest. Um, when I used to teach scuba when I was in college at the University of Florida, and we would teach in the pool for a lot of the lessons until they were ready to go out in the wild or the ocean or whatever. Um, so we would do kind of skills and things like that, and sometimes we would just let them like play underwater with their scuba gear. And so if I wanted to get my students' attention, um, I would um, I would make one hand flat, and then I'd make the other hand into a fist, and I would hit my fist kind of like that. I don't know if you guys can hear that. And underwater, that's really, really loud, and it like echoes around the whole pool because it hits the walls and comes back, and it makes this really loud noise. And what it does is the kids can hear it, and then when they hear it, they kind of spin around in a circle, kind of looking for me where I'm coming from. And the reason they do that, they can hear it, but they can't tell how far away it was because sound travels so fast in a liquid, which is why that noise, it sounds like nothing on land, is really loud underwater. Um, and so if you think about a gas, when a sound is coming towards your ear, if it's coming from over here, let's say the left, it's going to hit one ear and then it's going to hit the other one just so slightly after the first one, which gives you an idea of where it's coming from because your brain knows that it's hitting this left ear first. It's hearing it in that ear first and then the next one, so it knows it's coming from over here. Okay, well, underwater, even if you're coming from over here, it travels so fast that it hits both ears at the same time, so your brain can't tell where it's coming from. And that's why my students would spin around and look for me. And once they found me, then I could, tell them whatever I wanted to tell them, you know, and be done with it. But they couldn't just tell where I was coming from based on that noise because sound does travel so fast in a liquid. Now, the speed of sound at 0 degrees Celsius is 331 meters per second. Again, that's something I'd have to write on a note card and memorize. And then it increases by 0.6 meters per second every degree. And it actually decreases by 0.6 meters per second for every degree as well. So let's talk about the Doppler effect. So the Doppler effect, we mostly think of the Doppler effect when we think about sirens, like ambulances and things like that, but it is not a purely sound phenomenon. It can be used with other types of waves as well. So if I have my ambulance and my ambulance has a siren on and it's going towards my person who is not moving, okay, the pitch is going to increase. The pitch is going to go up. Okay? And then as it moves away from me, the pitch is going to decrease. And that phenomenon is the Doppler effect. That is the best example of the Doppler effect. If you want to watch something funny, look up Big Bang Theory Doppler effect. Sheldon does a really good Doppler effect. He goes as the Doppler effect for Halloween one year. Okay. And that's also why when you're driving down the road or you're riding with your parents and you hear an ambulance, as soon as you hear it, you don't know where it is, right? You like look around for it. Oh my God, is it coming towards me? Is it on the other side? What's going on? Where is it at? Do I need to pull over? You have to hear it a couple times. You have to hear that siren a couple times in order to tell if the pitch is increasing. And if it's increasing, then you know that it's coming towards you, and you're probably going to have to pull over unless it's on the other side of the road. Or if the pitch is decreasing, then you know it's going away from you, and you don't need to worry about pulling over. You're good to go. Okay. So that's the Doppler effect. That's why we have to wait a little bit in order to tell, because we have to hear that siren and whether the pitch is increasing or decreasing. Some other things that use the Doppler effect. Scientists actually use the Doppler effect to measure like stars and how fast or slow they're moving, and if they're moving towards us or away from us. And they use it with light. Um, they can kind of tell. Doppler effect, when you talk about your Doppler radar, right? Your Doppler radar forecast. Um, someone I think did a discussion post where they talked about um, how a police radar was the Doppler effect. So that was, another example. So it's not just sound waves; it can be other types of waves as well. And then one of the things they talked about in our videos was the sonic boom. If you have an airplane, this is my airplane. I'm not really a great airplane drawer. Um, this is an airplane going the speed of sound. This is someone with this poor malformed head. Um, Maybe I'll put like a baseball cap on this person, and then it looks like it's not too bad. So it's a sonic boom is a cone of high pressure air spreading until it reaches the ground. Um, so it depends on where you're at, and as to when you're going to hear it. If you were like sitting in a tree right here, I know an airplane is not going to be where the tree is. Then you would hear it before this guy. One, because this guy's far away, but two, because the person in the tree is higher. So it's like this cone of high pressure air that gets bigger and bigger until it hits the ground. Which is why, if this guy right here were to look up, he's not going to see the airplane right there, right? The speed of sound is fast. Okay? So the airplane has already passed that spot. And so he would have to look this way in order to see the airplane. It wouldn't be straight above him. Okay? So I think there's some sort of question that says something like, if you look up when you hear a sonic boom, are you going to see the airplane? No. If you look straight up, you're not going to see the airplane. Then we can talk about standing sound waves. We talked a little bit about this in the wave unit, but now we're going to talk about it again in the sound unit. These could be like strings on a guitar or something like that. These two sides, these are known as nodes. And then this middle is an antinode. Okay, and you're always going to have one more node than antinode on these type of waves because you have to have at least those two nodes at the edge. Okay, so for the first harmonic, you're going to have one antinode and two nodes. For this second harmonic, you're going to have three nodes and two antinodes. For the third harmonic, you're going to have 1, 2, 3, 4 nodes, and then 1, 2, 3 antinodes. For the fourth harmonic, you're going to have 1, 2, 3, 4, 5 nodes, and 1, 2, 3, 4 antinodes. Okay. Something else that's kind of important. So the fundamental frequency is that first one. Okay. And that's known as the first harmonic. It is not known as any overtone. Okay, so I'm going to call it the first H. Okay, then that next, and it's also in the formula, it would be like F1. Okay, then your next one is your second harmonic, or your first overtone. Okay, so I like to talk in harmonics because they go 1, 2, 3, 4, and the first overtone actually starts at the second one. And so it's easier for me if I'm thinking, oh, okay, what's the second harmonic? I know that's F2. So if I want to do math, I would do 2F. Okay, our second overtone is actually our third harmonic, or F3. Okay, and then we can talk about some of these sound waves. If your frequency is increasing, your period is going to decrease because these guys have an inverse relationship. And then there's all sorts of questions, or people always wave speed. Okay, so wave speed, frequency does not affect your wave speed. Wavelength does not affect your wave speed. Amplitude does not affect your wave speed. The things that affect wave speed, why will it not make a food? The things that affect wave speed are temperature, and we looked at that, right? We did some math with it based on the temperature, right? Your wave speed changes. And then also the medium, right? And we discussed that as well too, right? Sound travels faster in a liquid than a gas, right? That's the medium. Okay, so these are your two things that affect your wave speed. Your temperature and the medium. None of these other things. Okay, my kids would always miss questions about that too. So remember your F1 is your fundamental or your first harmonic. Your F2 is 2 times F, and that's your first overtone or your second harmonic. Your F3 is your second overtone or your third H, third harmonic. F4 is your third overtone. So your overtones are always like 1, whatever your frequency is, -1. Like whatever frequency you're on. So if you're in your fourth frequency, -1 would be your third overtone. F5, 5 minus 1 is 4, fourth overtone, or a fifth harmonic. Okay, so then if your F is 500 hertz, then F1 is 500. Whoa, stop that. Um, okay. Then if F2, 2 times F, so we've got 2 times 500. We're going to have 1,000 hertz for our for F2. For F3, we're going to have 3 times 500. So we'll have 1,500. For F4, we'll have 4 times 500, which is equal to 2,000. F5 would be 5 times 500. If we wanted to do F20, we would do 20 times 500. And so as far as math goes, I think these are pretty easy. And so that's how you calculate your different harmonics.